Good morning, everybody. It is a very big surprise for me, really, to have the chance and to have this. It's a great honor and big pleasure for me to give this public talk here. I decided to change a little bit the name of this presentation, Mathematical Models in Engineering, and I'd like to talk more about this application of these models. And you see, first of all, I tried to find the definition of these mathematical models in internet, and I found more than 40,000 definitions. And after some hesitation, I decided to find my own definition of what does it mean, mathematical model. It's much more easier comparing with, instead of checking all these 40,000 other definitions. And it seems to me that the best definition of mathematical modeling is as a mathematical reasoning which express or explains some non-mathematical phenomena. If this mathematical reasoning explains some mathematical phenomenon, it's not the model. It's just some mathematical consideration. But if you study some non-mathematical phenomenon and try to use the mathematical language, I think it's a mathematical model. And usually in history of mathematics, it's well known that the first mathematical model was invented by Isaac Newton in his well-known book. But if we say that, for example, geometry is the part of mathematics, in this case we can find the mathematical models which were invented many, many years ago. And the first example which I found was this one. Yeah, it's some geometrical construction. And first, I am sure that the people who constructed it, first they used some mathematical model like this one. You can make it from paper, you can study all the properties, you can understand how many blocks you need to construct it, and after that, after the investigation or explanation of all these mathematical problems, you can duplicate or multiplicate it and construct a lot of these pyramids like the first one. But however, I would like to say that for good mathematical model we need very good experimental data and we need some good mathematical explanation. Usually the mathematical model we can write in this form: AU equals F. F is some kind of information which we can find using the experiment. U is the characteristic which we are looking for. And A is something which connect U with F. A is a mathematical model. Usually we can give another definition of this mathematical model, but it's obviously more popular is this one. And sometimes we are sure that if we construct this A, the problem will be solved. But sometimes it's not correct. And about the data, I would like to say that the first mathematical model was made by Newton, Sir Isaac Newton, to explain the moving of the planets or the moon around the Earth or the planets around the sun. But he needs some precise data. And these data were first time all the measurements, the precise measurements were made about 600 years ago in the observatorium of Ulugberg. This is a picture of this observatorium. The main part of this observatorium is this sextant, which allows to measure the coordinates of all planets of all the stars with a very high, how to say, very, very precise, yeah. And But there was one problem. There was not mathematical model which can explain how to use this data to predict the moving of all the planets and so on. And this mathematical model was constructed later using the same data which were repeated. After 150 years after this Ulugh-Beg observatory of Ulugh-Beg was in city Samarkand 600 years ago. And after 150 years, these results were repeated in observatorium by Tycho Brahe near the Copenhagen in Denmark. This is a building of this observatorium of Tycho Brahe. And his assistant, Johann Kepler, who used this data for the constructing the mathematical model. The first model was made, model of the moving of planets around the sun was made by Copernicus, you know this, the modern model. But Copernicus decided that all the planets are rotating around the sun following some circles. But only because of the measurements which were made in this laboratory, they understood that there were no circles. It was some ovals, some very strange curves. And Johann Kepler was the first who said that they are the ellipse. You see, this is an ellipse, there is the sun. But why they are rotating following this curve which we know as ellipse? Nobody can explain it. It was just some constatation of some result of experiment. This is a book of this is a well-known book of Sir Isaac Newton, Philosophiae Naturae Principia Mathematica, and here we were given the explanation of all these phenomena. His mathematical model, this differential equation, and R is the coordinate of this planet, T is time, M is the mass, and F is the force. But what kind of force we need to use, it was not known. There was suggestion of three scientists in Great Britain. They were sitting in some pub or cafe, nobody knows exactly, maybe near in London, and they were discussing maybe F is inverse proportional to, you see this, oh sorry, inverse proportional to R square. It was suggested by Hooke, you know this Hooke law in theory of elasticity, and he said, I'm sure that it's R square, but I cannot prove it. What does it mean to prove it? If the force is inverse proportional to R square, in this case the trajectory must be ellipse. I cannot prove it. And next was Wren. He was architect. You know, he's building St. Paul Cathedral in London. He agreed, but he couldn't prove too. And the third was Halley. Halley, you know, because of Comet Halley. He was 27 years old. Next day, Hooke said, I will give some money, about 100 pounds, to anybody who can prove it. And next day, Halley went to Cambridge and asked Newton, if there will be C over R square, in this case, what will be the trajectory? And Sir Isaac said, at that time he was not Sir Isaac, just Professor Newton, he said it will be ellipse. And Halley was very surprised and asked, why do you know that? And Newton answered that I calculated it. And Halley asked him to write this proof to publish it. And it takes about 2 years to write this book, which I showed in the beginning. And this is the beginning of the implementation of mathematical model to some explanation of some natural phenomena. You see, we need some differential equation, and we need some suggestions, and we need some data. This is solution. R is this fraction, And it's well known to all the students from engineering faculties that if epsilon is small, is it ellipse? If epsilon is big, is it hyperbola? If epsilon is 1, it's a parabola. It means that all the objects will be going to the will be follow the path which are only these 3 curves here and nothing else. If there is no another force, we cannot explain the trajectory of a rocket or some another object, but if there is a planet or the moon, you can explain it. After that, everybody decided that, and it was Laplace who said that if you will give me some data, I will calculate everything. But later, the mathematician understood that it's a mistake. You can have a lot of data, very precise, but it's impossible to calculate the future of some process. And it was discovered by Adamar about 100 years ago. And but he said, if we meet some mathematical problems where the very good calculations and very good experimental data they do not allow us to find good solution, in this case, this problem is not important. You cannot meet such a problem in the real life. And stop to study these problems. Just after that, there were found 3 problems. I would like to share you with these 3 problems, which seems to me very important. One of them is the predicting of the how to find the temperature. It's well known the heat equation. Almost all students in engineering faculties, they know that heat equation. If you have the heat equation, if you know the temperature today, you can calculate the temperature which will be tomorrow. It's very easy. But the question was another inverse problem. We know the temperature today. Can you find what kind of temperature was yesterday? It is an ill-posed problem. You cannot calculate it. It's very strange. Another problem, you know the electromagnetic wave on some boundary. Can you find this electromagnetic wave inside this medium, for example? It's impossible. So you can calculate it, but the mistake, the error will be very bad, very big. This problem is very important in electromagnetic prospecting. When you are looking for oil, for gas inside the earth, you cannot make the holes everywhere. You just can measure the electromagnetic wave on the surface, and after that you must give some recommendation. Is there inside the oil or gas, or there is nothing? And the third problem was integral equation. Integral equation, you know the integrals along any lines. Can you find the density of some medium which are integrated? And this is a very strange problem, and nobody knows why we need to study it. It was discovered, this problem was first investigated by German mathematician Radon, Johann Radon, 100 years ago at the same time. But later it was used for computer tomography. The base of computer tomography is this Radon transformation. You see, I give you, now I give it more precise maybe. This is a Cauchy problem for Laplace equation. And this explanation why these solutions are not precise. You see, for example, we know this is a medium. We try to find something here. Maybe there is oil, maybe there is a gas, but we can measure the electromagnetic waves or field only here, only on this border. We cannot measure it inside, but we need to predict what's inside. In this case, we study the problem. We call them Cauchy problem for Laplace equation. It's not correct problem. If you use the computer will calculate some, very often calculate wrong. This was explanation. You see the data. maybe exponentially small. E in the power of minus is n squared. But the solution, because of this n, grows exponentially. N is bigger than n squared. Because of that, it's this initial data tends to 0, but the solution tends to infinity. It's very strange. This is a problem of heat equation. This is a heat equation. And again, the explanation is the same. You see, the temperature is the exponent of minus k squared T. If T is positive, what does it mean T positive? We try to calculate what will be temperature tomorrow. Tomorrow T means in these 24 hours plus. And we can calculate it very easy. But if we try to find the temperature for yesterday, for example, in this case T will be negative. And minus T is positive, it's exponentially big. And we cannot calculate this, cannot find the solution to this problem. It's very easy to understand from physical point of view. What does it mean, the temperature? Temperature is the velocity, average velocity of molecules of atoms inside some volume. You see, we have some atoms or some molecules, and they are very uniformly distributed, and we can calculate the temperature. But let us suppose that yesterday all the molecules were in one part and no one here. This temperature is very high, and this temperature is 0. And after that we open this wall, and they will be distributed uniformly. Can we calculate yesterday all these molecules were on this part or on this part using only this picture? It's almost impossible. It means that we can predict what will be the temperature tomorrow, but it's almost impossible to say what was the temperature yesterday. It's understandable from physical point of view. Sometimes it's possible, you see. For example, using this picture, you understand that maybe all the molecules were here, not here, because there is too small. Sometimes it's possible, yeah. And this is idea how to use mathematical methods to calculate it. And this is some explanation of mathematical approach. You see this model A, U is unknown, F is known. Usually U is A we call some operator. If A, U is better than U, we like these operators, they are very good integral operators. But for the equation, for the problem to find the solution, it's worse. Because if A is a very good operator, we are looking for U, and F is known, we calculate the F using some experiment, and after that we try to find U. If UA is very good, in this case F must be very good. For example, 5 times differentiable or infinitely differentiable function. But using the experiment we cannot find such smooth functions. Usually we have some not so smooth functions. It means that for these functions maybe the solution does not exist. This is the problem. You see, if you have too many data, you have more problems with finding solution. It looks very, very strange. If I continue my measurement, maybe after that it will be easier to find the solution. Just one example without any of this picture. I know that the process is like straight line. The graph is like straight line. And I calculated in 2 points, I found 2 points, and I draw this straight line. It's okay. But if I calculate in 3, 4, 5 points, it would be better. But all these 5 points are not on the same straight line. And how to find a solution in this case? This is the problem. More you know, less you can predict. It's very strange. Yeah. This is a third example, integral equation. What's the meaning of this integral equation? You see, we have some object with some density, this is density. And we integrate the intensity of this electromagnetic beam. We know in the this intensity in the entrance, and we know in the when it leaves this object. The difference is this integral. It uses it in the computer tomography. We know the beam which we send to some object, and we know the resulting beam. But after that, we try to explain what's to find this density. What does it mean to find? To find the shape, for example. Yeah. Yeah. We usually use something like X-ray, and in modern computer tomography, they use it not only one ray, but the array of this ray. You see, for example, many rays, they were sent in this direction, and there is some screens and sensors which detect and calculate the intensity. And after that, we try to find what is inside. It's a mathematical problem which was studied by German mathematician Johann Radon. Yeah, it's an ill-posed problem. After that, we calculate something. We have the usually computer cannot solve the integral equation, only linear algebraic equations. But we can transfer this integral equation to the system of linear algebraic equation using, for example, Simpson formula to calculate this integral. When we calculate this integral using Simpson formula, we have some system of linear equations. I will give only very simple example. When we have some problems, just calculating very simple linear, to find the Radon transform, inverse Radon transform, to find this solution for computer tomography, we need to solve about 1,000 linear algebraic equations with 1,000 unknowns, the coordinates of these points. And I consider only 2 equations with 2 unknowns. Very simple, you see. And lambda, we try to find this lambda is unknown. We try to find it using experiment. Experiment shows that lambda is about 200, and the error is 1. It means that lambda is 200 plus minus 1. Can we find x and y? Just let us suppose that, for example, lambda is 0. In this case, lambda is 200 and error is 0. In this case, we have this equation, and this is solution. Very simple, you see, 5 and 0. It means that we have some object. Our suggestion for surgery, for example, after these calculations, I'll say to the surgeon that this object is over there. You can open something and find over there something bad. Yeah, but this is in case if lambda is 200. But let us suppose that lambda is not 200, but maybe 201 or 199, because the error is 1 plus minus 1. Just in case when it's 201, the solution 30 and minus 37 is its exact solution. Just compare with this solution. 5 and 0 when lambda is 200, 5 and 0, and 30 and minus 37 when lambda is 201. Okay, maybe it's another mistake. Maybe it's not 201, but maybe it's plus minus 1, minus 1. In this case, lambda is 199. In this case, you see this solution. Just compare these two. X 30 minus 37 and minus 20 and 37. And what kind of suggestion? I'll show you. This is my suggestion to the surgery. Maybe here. In case 201, or maybe here in case 199. The same equation, very simple, only two linear equations. But if we will calculate, for example, 1,000 linear equations, and inside these 1,000 linear equations, there may be 2 like this. Okay, maybe it's not good measurement. Now you see, I tried to measure it with very big precise. Lambda is 20 plus minus 0.1. It's how it's, you see, 0.05%. Less than one, how to say, it's a very precise measurement, yeah? And try again, 200.1. In this case, solution is this one. And if lambda is a little bit less, this solution, you can compare this one and this one. Y is minus 3.7, 3.7. Why? This precise measurement, they do not help. Just again, this here or here, I don't know what to say. Sorry. It stopped. I don't know why. Slideshow again. Yeah, okay. No, this one. This, okay. And usually we try to find the normal solution. Normal solution is if in this case, this system of linear equations, they have only one solution. Sometimes we meet some system which have a lot of solutions, infinitely many. In this case, we try to find the smallest is a normal solution. But this normal solution is, how to say, not good depending on the data. And it was the example of that. But the idea is, this idea was supposed about 50 years ago to regularize this equation. Instead of this equation, instead of this equation A U equals F, we change the model, something like that, with small parameter. And after that, we can find the solution which may be not exact, but very near to exact solution. This is some calculations. It's not interesting here. Oh, sorry. And we find a good solution using this regularization. I think that it's maybe it's very important to know for engineers that you need to check this mathematical model which you use, and to try to find some improvement of this model for better calculations. Second part of my lecture is about the importance of these all mathematical calculations, especially for engineers. What do I mean? It's necessary to know mathematics. That's the main idea. I can give you only 3 examples. I prepared, I can give 100 examples, but I decided to give only 3 of them. And not because they happened in some countries where the people do not know mathematics, no. 2 examples from United States and 1 example from Great Britain. And from the companies with very high technology. And the consequences in all these cases were awful. The first example is Hyatt Regency walkway collapse. In Hyatt Regency, they decided to build this in Kansas City hotel, and inside the hotel there was 2 walkways, one under the other. You see? It was killing 114 people and injuring 216. In 1981. It was not in the 18th century. It was in 19. I remember that at that time I was a professor at the university. What happened? You see, it was before. They made 2 walkways, and they are connected with the ceiling. You see, using these rods here. This is after collapse. Because of wrong mathematical calculations. Very simple calculations, I'll show you. You see, the first suggestion was the following: this rod and these two platforms fixed by nut, one and second. And the company said that it's very difficult to make this very long rod. Maybe we'll prepare two of them, one and second, and connect this way. And after that, it will be just the same as the first one. But you see, this is critical. This nut now is supporting only one platform, yeah? And the weight of this platform is, for example, P. And the force is P for this nut. Here, the same nut, you see, the same, is supporting two platforms. Because this one, but this one is connected to that. It's just like a climbing the mountain. You are climbing using the very big some device. For example, you are climbing this mountain, and you are taking the leg of your friend who is first. Yeah. In this case, it will be very difficult to your friend. Yeah. Just the same. Sorry. This difference is understandable. You see, again, for this nut, it's nothing. It's the same. It supports only one platform, and this is only one platform. But this nut is supporting only one platform, but in this case, two platforms. There is a force equals P, and this force equals to 2P. And this was the result of this collapse. This was not the result. The result of collapse was because of this mistake. Very simple mathematical mistake. And how many victims? Another example, it's a corner crack. It's very easy to calculate the, you see, mechanical stress. Usually it's not just exact this equation, but very similar to this equation. And the force is a gradient of this solution. And if we calculate in different domains in some angle, we can find this solution. I'll show you. Yeah. What's the difference between the solution inside this domain and inside this domain? It seems that it's the same. Almost the same, but you see, this angle is 90 grades. This is about 90, and this is about 90, and this is 2. But this angle is 270. What's the difference? Again, if the angle is less than pi, it's okay. But if the angle is more than pi, there is some stress because of these calculations. Yeah. You see, it depends on n over mu. After differential, if it's more than 1, in this case, the derivative is a smooth function. But if it's less than 1, the derivative is a singular function. The derivative is the stress. Now it's understandable that the stress in this point is 0. But the stress at that point is very big. Almost, it's a singular point. It tends to infinity. That's its explanation. And in case if there is no angles, no stresses, just consider this plate. It means that the first one is this one, and there is no stress at all. Second is this part, and this is the stress, very big. You see this r is in denominator, and r tends to 0. R is the distance from this point to this one. And when r tends to 0, the stress tends to infinity. This is solution here. It means that the very big points, we have 2 points where the stress tends to infinity. It's a very simple, how to say, not so simple. Oh, again, excuse me. Just a second. I cannot find this. There is no connection. Again, yeah, slideshow. Yeah, thank you. You see, this is example. It happened after the Second World War. It was a well-known, the first jet of passenger jetliner. It was a comet, DH-106 Havilland comet, in July 1949. It's a first flew. But first commercial flu was after some years. Yeah, 1953. You see, you can find it. Calcutta International Airport. The first accident. They said it was because of thunderbolt. There was a lightning, and because of that. But you see, just next year, in January, again, from Ciampino, near to Rome, in Italy. Again, the same. You see, at that time there was a thunderbolt too, and they decided because of that. And next, just after 3 months, April 1954, again, near to Rome, to Cairo, there was no thunderbolt. The weather was excellent, and the same. And after that, they stopped it and decided to investigate what was the reason, why it happened. Again, if we consider the solution inside the, without no angles, you see, just it's outside the circle. In this case, the solution is very good. What was the reason? They put the airplane inside the pool, filled it with water, and changed the pressure. And they found that after some time, all the windows were broken. The stress was, you see, these windows are rectangle. And they were broken on all these 4 angles. And the stress begins, the crash begins from this window. After this investigation, they changed the shape. You see, you can see now they are oval. It's the same airplane, comet. And because of that, there were these awful accidents. Because of wrong calculations. It was very easy to predict it if they calculate the stress of this corpse of the airplane. They put it inside the pool and changed it. You see, there is a fatigue of metal, and usually the metal can be used after 3,000 changes of pressure. 3,000 changes, it means if 3 per day, 4 per day, it means about 1 or 2 years of flight. It happened just after 1 or 2 years of flight. Why it was not before? Before, all the airplanes have the same, they have the same rectangle windows. Because before that, they did not fly with a very big height. And they do not need to change the pressure, difference between the pressure inside the airplane and outside. It was the same. But this airplane was flying too high. And because of that, they have big pressure inside and very small pressure outside. There was a difference. And because of this difference, there is fatigue of metal and the result. Now all these airplanes are calculating very careful. It's the second example. And the third example is auto-oscillation. You know this resonance. If you consider the problem wave equation, and if the force, you see this force F, depends on T, there is a solution. Let us suppose that this force F depends on T periodically. like harmonic. In this case, the solution is the following. If some eigenvalue of own frequency coincides with omega, in this case, the denominator may be 0, must be 0. And the solution is a little bit different. What's the difference? There is a t, you see? It's like just like to differentiate this function when omega tends to some lambda. In this case, we have the derivative with respect to omega, and in this case there is a additional multiplier t. It means that the amplitude is growing. This is a resonance. But again, the resonance may be only in case when this outer force depends on t periodically with the same frequency omega as eigenvalue, as own frequency. But sometimes f may be not depending on t, but however there is something like resonance, but it's not resonance. Resonance only in case when the f is periodical with the same eigenfrequency, how to say it. But sometimes it may be not. You see, it's just, I give this example. In string instruments, the friction force between the bow and the string maintains self-oscillation. You can play the violin without oscillating, but however there will be sound. This is outer self-resonance. And again, this force doesn't depend on t, but the result, this is the main part, but there is another part which depends on t. And in this case, maybe there will be additional, you see, there is no oscillation with respect to time, but there is. And what's the result, self-oscillation? You need to calculate them too. Sometimes they are very awful. And I would like you to show this Tacoma Bridge. It's a suspension bridge. It was made in 1940. It opened at July. Yeah. And collapsed. And it was the third longest suspension bridge in the world in terms of main span length, behind the Golden Gate Bridge and the George Washington Bridge. I would like you to show the picture. It looks like a resonance, and many people, they said that it was a resonance, but the wind was with the constant speed, with constant velocity. In this case, it's not a resonance. Why it happened? Because of some wrong calculations. You can find a lot of explanations, including mostly they connected with resonance. It's a wrong explanation. Some explanations are correct, but I try to give some another explanation, maybe. Just a second. A professor who was invited to explain it, he made them shoot some movie, and this movie is very popular. You can find it on the internet. Sorry. This is this movie which, sorry, there is no sound. How to find this sound? I don't know. This one, yeah? This, no? No, how to make it bigger? To move something. No sound, yes? You see, this is professor, yeah. And this bridge was made from steel. It's not plastic. No, okay. And this is the result of these oscillations. I mean, the sound, there was an explanation in English to the students of the engineering faculties what happened. But he said nothing about the resonance and self-oscillation. And I try to explain why it happened. You see, we know the Bernoulli Principle. This is something like wing, and there is a wind in this direction, moving of air, and because of that, the pressure from up and down, they are the same. And because of that, this wing is not moving. Why there is additional pressure sometimes? If the way of the air is longer, in this case, if there is no turbulence, in this case, the pressure will be less because of the conservation law. The energy is constant, the energy is kinetic and potential. Potential energy is pressure, kinetic energy is speed, is the velocity. If velocity is higher, in this case pressure is less, and there is a difference of. But for this shape, the way is the same, and because of that the velocity is the same. If we change it to this shape, it's like a wing of airplane. In this case, this path is longer, this is short, and the velocity here is higher, and the pressure is less. It was first explained by a Russian physicist, Zhukovsky. You can find the critics of this idea, for example, in Wikipedia. Wikipedia is a very nice site. You can find a lot of information. There is only one problem, about 90% is wrong. But how well altogether they are very interesting. My recommendation, read this Wikipedia, but do not try to use it when you prepare to exams, for example. Yeah. But you can find a lot of information. Yeah. And because of that, this wing moving up, if there is some speed. And let us suppose that we have two wings. In this case, there is additional pressure. If they are too small, again, in this case, there is additional pressure. Moreover, there is another problem. If the wind goes in this direction, here maybe the wind will be, the velocity will be zero, and the pressure here will be higher. The pressure at this point and this point, they will be different. And what's connection with Tacoma Bridge? This parapet in Tacoma Bridge. Usually, these parapets are transferable for the wind, for the air. But they were solid. First time when this suspension bridge was made with solid parapet. It was because of a recommendation of some, Russian engineer who said, we have a lot of these materials, you can use it, it will be much cheaper, yeah. And they were, you see, they were not transparent, they were solid. And because of that, there was effect of these wings. You see, you can say it's not so big, but small wings of the one airplane, they can take to the air about 100 tons of metal, yeah. But this area of the bridge is 100 much bigger than the wing of aeroplanes. You can understand, you can imagine what was the force of this wind, yeah. And this is this bridge from the, if you will make the picture from the top. And the simple calculations shows that the solution will be like this one. There are, you cannot see it, yeah. This is a formula for oscillations. And in the middle, when the oscillation is almost zero, it's rotating around this axis. Yeah, I can explain it again to if I'll show this from the beginning here. Yeah, just pay attention that it's opening ceremony. Just after the opening ceremony, after some hours, it happens. And everybody escaped, but there was only one car with one dog inside. And this professor he decided to help to the owner of this car. The owner was afraid to go to his car, and he went to this car he tried to help to escape this dog inside, but dog was afraid to leave the car, and dog died together with this car. Just a second. You see, this lane is more safe, and the professor was going just using this lane. I said about the y is 0. Only the victims was this car and the dog inside. It was oscillating about 4 hours before collapsing. Yeah. Next, after some time, after the Second World War, it was reconstructed. But again, sorry. No, this one. Too many slides, sorry. Yeah. This is the right solution. And you see this new bridge. Next, it was constructed the second bridge, you see, parallel to this, the first one. And this is parapet. You can compare it, not solid. And because of that, there is no problems. It's only mathematical mistake. And all the idea of my lecture today was to explain to the students of engineering faculties that mathematics is very important, not only to pass exams, but to use it in their future work. Thank you for your attention.
Ladies and gentlemen, now I would like to call upon Professor Dato Dr. Kamil Arifin Muhammad Attan to present the token of appreciation to Professor Dr. Shavkat Alimov. Please welcome. Thank you very much. Ladies and gentlemen, in conjunction with 70th birthday of Professor Shavkat Alimov, I would like to call upon once again Professor Dr. Shavkat Alimov, Professor Dato Dr. Kamil Arifin Muhammad Attan, Associate Professor Dr. Syamuddin Zainuddin, and Professor Dr. Abdul Malik Rahimov to the stage for cake cutting ceremony. Please welcome.